Good afternoon, everyone. Today I'll be presenting my work on fault detection of industrial gas turbine engines. My name is Gary Salinas, and I'm a graduate student in the data science program at the University of Colorado-Boulder. My project focuses on using machine learning techniques to classify faults in gas turbine engines and identify which features contribute most significantly to these fault conditions. Industrial gas turbines serve as a backbone of rotating machinery systems across a wide array of industries, playing a particularly pivotal role in midstream pipeline operations where they power compression systems. The impact of turbine failure is substantial, often leading to severe operational disruptions, extensive downtime, and skyrocketing maintenance costs. The pressing challenge we encounter is the accurate classification of potential faults before they escalate into catastrophic failures. Fortunately, modern turbines are equipped with an array of sophisticated sensors that generate a wealth of data, presenting a unique opportunity to develop cutting-edge fault detection systems. Our innovative approach harnesses advanced machine learning classification techniques complemented by feature engineering to uncover and analyze patterns associated with various fault conditions. Our ultimate objective transcends mere fault classification. We aim to pinpoint the specific features, whether they be singular sensor readings or strategic combinations thereof, that have the most significant impact on engine faults. This valuable insight can empower maintenance teams, equipping them with the knowledge needed to implement more targeted inspection and repair strategies, ultimately enhancing the reliability and efficiency of turbine operation. I would like to take a moment to outline the achievements I have made throughout this project. I have successfully developed an advanced fault classification system utilizing the Kaggle gas turbine engine fault detection dataset, which serves as a crucial resource for understanding engine performance anomalies. My approach involved constructing a robust preprocessing pipeline that effectively incorporates techniques such as feature scaling and engineering. These methods have significantly enhanced the clarity and quality of the data, allowing for a more accurate analysis. To further refine the model, I applied dimensionality reduction techniques with a focus on principal component analysis. This not only improved the overall performance of the model by minimizing noise, but also ensured the retention of essential information. I utilized a variety of classification algorithms paired with K-fold cross-validation to evaluate models and ensure their reliability. One of the most rewarding aspects of this work has been the identification of key features that play a significant role in indicating fault conditions. This discovery provides maintenance teams with valuable insights that can inform their practices and improve operational efficiency. The combination of precise classification and an in-depth feature important analysis truly encapsulates the core value of my work and its potential impact on turbine maintenance strategies. To truly grasp the significance of my work, it's essential to explore the business impact of undetected turbine faults. When these faults go unnoticed, they can trigger a cascade of issues resulting in costly downtime and repairs that can easily escalate into millions of dollars. This not only affects the company's financial health, but can also disrupt operations and the safety of the workers. From my perspective, a critical challenge lies in pinpointing which sensor reading serves as the most reliable indicators of potential fault conditions. With an array of data available, including intricate details on temperature fluctuations, pressure variations, and vibration levels, distinguishing the subtle yet vital signs of impending faults is no small feat. Current monitoring systems often struggle to decipher the complex relationships between these operational parameters. It is not immediately apparent which specific combinations of these readings genuinely signal an impending fault. This ambiguity can lead to missed opportunities for early intervention. My ambition is to create a classification framework that not only delivers precise fault detection, but also provides valuable insights into the significance of different features. By achieving this dual objective, I aim to ensure that my models do more than just predict faults. They will empower maintenance teams with a deeper understanding of the underlying causes, enhancing their ability to prevent future issues and optimize operational efficiency. My approach builds on extensive prior research in this field. I found that Babu 2016 emphasized the importance of feature engineering, particularly the extraction of time domain and frequency domain features from temperature and vibration data for effective condition monitoring. I have observed that parameters such as pressure ratios and temperature differentials have consistently proven useful for early failure detection. For instance, Malhotra 2016 utilized long short-term memory networks to identify temporal patterns, while I also recognize that simpler statistical techniques like rolling averages and train decomposition can provide valuable insights. In terms of outlier detection, I have discovered that techniques such as isolation forest and DB scan are effective in identifying anomalies that could indicate development issues. Additionally, recent insights from the Internet of Things analytics highlight the growing demand for interpretable and scalable predictive maintenance solutions, which reinforce the relevance of the methods I have chosen. For this project, we use Kaggle gas turbine engine fault detection dataset, which consists of 1,386 samples and 10 continuous variables. These features include critical measurements such as temperature, torque, pressure, vibration, RPM, and power output. The target variable is a binary fault indicator where 0 signifies regular operation and 1 indicates a fault condition. It is important to note that the original dataset contained a continuous type of fault measurements that I transformed into a Boolean type to frame the problem as a classification task. This dataset is particularly valuable because it represents real-world operational data from industrial turbines, not just theoretical or simulated data. This provides a realistic test bed for our fault detection approach, ensuring its practicality and applicability in real-world scenarios. My methodology follows a structured pipeline approach. I start with data pre-processing to address missing values and ensure high data quality. To ensure that all features contribute proportionately to this analysis, I use feature scaling with standard scalar, regardless of their original units of measurement. A critical step in my process is feature engineering, where I create domain-specific ratios and combinations that more effectively capture the underlying principles of turbine operations. Next, I apply principal component analysis, PCA, for dimensionality reduction, simplifying the feature space while preserving essential information. Additionally, I implement outlier detection using isolation forest and DB scan to identify and manage any anomalies in the data. Finally, I train multiple classification models and evaluate their performance using k-fold cross-validation, ensuring a robust assessment. This comprehensive approach enables me to develop accurate and interpretable models. Feature engineering is one of my most significant contributions to improving classification performance. Utilizing my domain expertise and knowledge of turbines, I developed several types of engineered features. These features include pressure ratios, which capture the relationship between pressure measurements at different points in the system, and speed to power ratios, which help identify when a turbine consumes excessive energy relative to its output. These engineered features are particularly valuable because they are strong indicators of early fault conditions and provide actionable insights for domain experts. When a specific ratio falls outside the expected parameters, it directs maintenance teams toward areas that require investigation. My results demonstrate that these engineered features significantly enhance model performance while also improving interpretability. After scaling my features, I applied principal component analysis to reduce dimensionality. This step is crucial because it helps eliminate noise, reduces redundancy among features, and makes the dataset more manageable for my models. I carefully selected the number of principal components to retain, ensuring that I preserved at least 95% of the variance in the original data. This approach strikes a balance between simplification and information preservation. An additional benefit of PCA is that it enhances my ability to visualize class separability, making it easier to understand how well my models distinguish between normal operation and fault conditions. Furthermore, the reduced feature space improves model training efficiency without sacrificing performance. I conducted an in-depth exploration of advanced methods for anomaly detection, focusing specifically on two influential techniques, isolation force and DB scan. The isolation force algorithm excels at identifying anomalies by creating multiple random trees that split feature values. In contrast, dbScan distinguishes itself by utilizing a density-based approach to cluster data points. It identifies operational anomalies by examining the local density of points, thereby effectively detecting highly clustered data regions while making sparse regions as outliers. Once I identified the outliers through these two methods, I generated additional derived features based on the detected anomalies and incorporated them into the original dataset. I implemented and compared four different classification algorithms, each with its own strength. Logistic regression served as the baseline model, offering high interpretability and computational efficiency. I chose the random forest classifier for its effectiveness and machinery diagnostics and its robustness to outliers. Support vector machines have also shown significant efficacy in detecting faults in rotating machinery, as evidenced by numerous studies. Lastly, I selected XGBoost, a gradient boosted implementation for a strong performance and classification task. By comparing these diverse approaches, I aim to gain a better understanding of the trade-offs between model complexity, interpretability, and performance. To ensure a thorough evaluation of my models, I implemented k-fold cross-validation. This method divides the dataset into k subsets. In this case, I used 5 subsets. I trained the model using k-1 subsets and validated on the remaining subset, rotating through all possible combinations. So in this case, I trained the model using 4 subsets and validated it on the remaining subset. I assessed performance using several metrics. Accuracy provides an overall measure of correctness, while precision indicates how many of my optimistic predictions were false. Recall reflects how many actual faults I successfully identified, and the F1 score offers a balanced measure that combines precision and recall. Additionally, I perform hyperparameter tuning using grid search to optimize the performance of each model. Throughout the evaluation process, I emphasize feature important analysis, as understanding which features drive prediction was a primary objective of my work. SVM, support vector machines, emerged as the most effective model for machinery fault detection, demonstrating strong predictive performance across key metrics. Logistic regression offered the highest interpretability, making it valuable for understanding feature impacts. By combining different modeling approaches, we leveraged the strengths of multiple algorithms to enhance overall reliability. Across all models, pressure ratios, temperature readings, and vibration measurements consistently rank as the most predictive features for identifying faults. One of our analysis' most valuable outcomes is identifying key features contributing to fault conditions. Temperature measurements consistently rank among the most important features across all models, especially in specific operational zones of the turbine. Pressure ratios, particularly those derived from raw sensor data, were highly predictive of fault conditions. Vibration readings also emerged as significant indicators, especially when abnormal patterns were detected. It is important to note that many of our engineered features ranked higher in importance than the raw sensor data, which validates our feature engineering approach. The objective of this project was initially to introduce time series analysis for fault detection. The goal was to leverage sensor data's temporal patterns to understand equipment behavior before failures occur. However, after extensive searching, I found it challenging to locate a suitable labeled time series dataset, leading me to use snapshot sensor data to develop my models. Despite this limitation, the value of online time series data for predictive maintenance is significant. Incorporating real-time sensor streams would enable models to adapt to dynamic changes in equipment deterioration, allowing anomalies to be detected in real time rather than relying solely on static data. Implementing real-time fault detection could enhance operational decision-making. Maintenance could be scheduled more efficiently, minimizing the impact on system availability and improving overall system reliability and utilization. Future research could focus on integrating streaming-based data analytics to create early prediction systems that identify issues and recommend effective mobilization schedules based on current operating conditions. Several promising avenues for extending this work include implementing SHAP for feature explainability, analyzing misclassification patterns, exploring ensemble models, evaluating models and simulated streaming data, and expanding the dataset with time-based features. In conclusion, I have successfully developed a framework that accurately classifies gas turbine faults and provides insights into the features that significantly contribute to these fault conditions. My approach to feature engineering has substantially improved classification performance, highlighting the value of integrating domain knowledge with machine learning techniques. By identifying key fault indicators, I offer actionable insights for maintenance teams, which can reduce downtime and repair costs and improve the safety of the system. This work demonstrates that even without time series data, static sensor readings can yield valuable fault classification capabilities when processed and analyzed appropriately. The combination of precise classification and feature-important analysis represents a significant advancement in industrial gas turbine maintenance practices. My project followed a structured timeline beginning with the proposal development and literature review on April 18th. By April 20th, I had completed data cleaning, feature engineering, and exploratory data analysis, establishing the foundation of my modeling work. On April 21st, I trained my first models focusing on random forest and logistic regression. By April 23rd, I expanded to include SVM and XGBoost models, completing my comparative analysis. The project culminated on April 28th with the final report and this presentation. This timeline demonstrates my systematic approach to developing and evaluating my fault detection framework. Looking ahead, there are several promising avenues for extending my work. I plan to refine my feature engineering by leveraging additional domain expertise, which may involve incorporating more complex relationship among operational parameters. Exploring additional classification algorithms, especially those tailored for imbalanced data, could enhance my performance further. Additionally, developing visualization tools for real-time monitoring of key features would increase the practical utility of my approach. Integrating my methods with existing maintenance scheduling systems is a crucial step toward practical implementation. Finally, I believe this approach could be applied to other types of rotating machinery, therefore thereby broadening its impact across various industries. I want to express my sincere gratitude to the University of Colorado-Boulder, the Data Science Department, for providing this wonderful learning opportunity, especially Professor Christine for her instruction. For those interested in exploring this work further, you can find the complete project, including code, notebooks, and documentation in my GitHub repository at the link provided on this slide. Thank you all for your attention today.